All right, so this is Mr. Walker, and we're going to continue with the 2.8 notes. This is part 2 of those notes, and again, it's on inverse functions. So if we look at the box at the top of your notes, and let's go ahead and read through all this. If f and g are inverse functions, then this statement tells you that's the case. All it's saying is that the g function is equal to the inverse of the f function. Look at number 2. It says that if xy is a point on the graph of f, then yx is a point on the graph of g. Because remember that f and g, those two functions, function f and function g, are inverses. So all you do, take xy, switch it yx, that point has to be on the inverse. And that's what we did yesterday. You just switch your x and your y. 3. With inverse functions, all of the x and y values are switched, so the graphical behavior in terms of x and y will also be switched. For example, the domain of f is the range of the inverse. So with the inverse functions, you switch the x and the y's. But what that does is it switches everything. So the domain of one function is the range of the inverse. And that's also true the other way. The range of the original function is going to be the domain of the inverse. And number 4, a continuous function will only have an inverse function if it is strictly increasing or strictly decreasing. If a function changes from increasing to decreasing, it will not have a function as its inverse. That's what the rest of it's saying. Let me show you what that means real quick. Let's say I have this function. It is strictly increasing. It is strictly increasing. Therefore, its inverse will be a function. This function is strictly decreasing. It's going down. Therefore, its inverse will be a function. This function is increasing and then decreasing. It will therefore not have a function as its inverse. This function is decreasing and then increasing. Therefore, its inverse will not be a function. And we saw that yesterday. Its inverse is going to look like this. And that does not pass the vertical line test. And so that's what this whole thing was saying. If a function is strictly increasing, its inverse is a function. If a function is strictly decreasing, its inverse is a function. However, if it changes from increasing or decreasing, or from decreasing to increasing, its inverse will not be a function. And it says it will not pass the horizontal line test. Remember, the vertical line test was a test on how you determine if a relation is a function. So for instance, if I had a parabola, it passes the vertical line test. Every vertical line only hits one point. It's a function. However, a parabola does not pass what's called the horizontal line test. If I draw a horizontal line, the horizontal line hits in more than one place. If the horizontal line hits in more than one place, the inverse is not a function. So if the horizontal line hits in more than one place, the inverse is not a function. All right, let's go ahead and do some problems. Example 1. Let's go ahead and run through these. Let f, so this is function f, be a continuous function. That just means there's no breaks or gaps, with selected values in the table. Well, it says below, but above. Let g be the inverse of f. So this is f. G is the inverse of that, such that g is the inverse of f. That's all that says. G is the inverse of f. Find the following values if possible. So let's go ahead and look at this one right here. These are compositions. This one is saying I'm going to put a 0 into the f function, and then whatever that evaluates out to, I'm going to put into the f function. So you always start with the second one, and you put that into the first one. All right? So I need to figure out what is f of 0. All this is saying is put a 0 into the f function. So I go to my f function, I put a 0 into it, and I see that a 1 comes out. So f of 0 is 1. So this is actually f of 1, because 1 is f of 0. And now I evaluate this. This is just saying put a 1 into the f function. So I go to my f function, I put a 1 into it, and I see that a negative 1 comes out. So that is going to be equal to negative 1, and that is your answer. That's going to be your answer on that one. Let's go ahead and look at that second one. B. B just says g of negative 3. That means I'm going to put a negative 3 into the g function. But I don't have the g function. Remember, the table is the f function. I'm putting a negative 3 into the g function. But do remember that g is the inverse of f. So follow this logic. Here's what I'm going to do. I look at the f function, and I notice that if I put a 4 into the f function, a negative 3 comes out. If I put a 4 into the f, a negative 3 comes out. So I know on the inverse, I flip these. On the inverse function, if I put a negative 3 in, a 4 comes out. Well, g is the inverse. So if I put a negative 3 in, a 4 comes out. So g of negative 3 is 4. Let me say that one more time, because it's really important that you understand that logic. G of negative 3. This is the f. G is the inverse of f. So I look at f, and I see that when I put a 4 in, I get a negative 3 out. So on the inverse, if I put a negative 3 in, I get a 4 out. So g of negative 3, which is the inverse, g is the inverse, I must get a 4 out. Let's go ahead and do g of 6. G of 6, I'm putting a 6 into the g function. This is the f function. But g is the inverse of f. So here's the logic. If I put a negative 3 into my f, I get a 6 out. So on the inverse, if I put a 6 in, I'm going to get a negative 3 out. Well, this is the inverse. So if I put a 6 in, I'm going to get a negative 3 out. That's going to be negative 3. Go down to D. D says g of negative 1. So I do this one first, and then I put whatever I get from that into this. So I need to figure out what is g of negative 1. Same logic that was applied up to here. I'm going to go to my f function. I see that when I put a 1 in, I get a negative 1 out. So on the inverse, if I put a negative 1 in, I must get a 1 out. Well, this is the inverse. So if I put a negative 1 in, I'm going to get a 1 out. So this is actually going to be g of 1. Because g of negative 1, if I put a negative 1 in, I get a 1 out. G of negative 1 is 1. So I'm finding g of 1. And I do the same logic. On f, on the f function, if I put a 0 in, I get a 1 out. So on the inverse, if I put a 1 in, I get a 0 out. Well, this is the inverse. I'm putting a 1 in, so a 0 must come out. That's the answer. Let's go ahead and look at this one. This one says the inverse of f of negative 2. This symbol we talked about a few weeks ago is just another way of writing this. Let me go ahead and write the equivalent form. It's the same thing as f negative 1, that's just the inverse of f negative 2. Those mean the same thing. I'm going to evaluate f of negative 2, put a negative 2 into the f. Whatever that comes out to, I'm going to put into the inverse. Okay, these two things are equivalent. So the first thing I got to figure out is what is f of negative 2? Well, this is f. This is f. So I can pull the value straight out. If I put a negative 2 into the f, I get a 3 out. So f of negative 2 is 3. So I'm actually need to find the inverse of f evaluated at 3. Because again, f of negative 2, if I put a negative 2 in, I get a 3 out. So I'm finding what is the inverse of f evaluated at 3. Well, this is f. This is f. And here's the logic. If I put a negative 2 into the f, I get a 3 out. Therefore, if I put a 3 into the inverse, a negative 2 will come out. And this is the inverse. So if I put a 3 into the inverse, a negative 2 will come out. And that's going to be equal to negative 2. And that's your answer. And finally, this one right here. This one is saying the inverse of f evaluated at negative 3. Well, this is f. It's not the inverse. This is just f. So here's the logic. If I look at f, I notice that when I put a 4 in, I get a negative 3 out. So on the inverse, if I put a negative 3 in, I must get a 4 out. And that's what I'm doing. I'm putting a negative 3 into the inverse. If I put a negative 3 into the inverse, a 4 will come out. So that is equal to 4. Let's go down to example 2. The function k is defined over the interval negative 4. Well, this is just saying right here, it's just saying that the x is between negative 4 and 11. That's all that's saying. So it's defined over this interval. We are going to let the inverse of k, that is the inverse of k. So let this represent the inverse of k. So again, the function k is this. It's defined on this interval, as you can see, -4 to 11. And this symbol just means the inverse of this. So this is the inverse of k. What is the minimum value of k? And what is the minimum value of the inverse of k? Okay, what is the minimum value of k? And what is the minimum value of the inverse of k? All right. So let's go ahead and look at this. Let's do this one. The minimum value of k. The minimum value of k is going to be the smallest y value. Well, this is k. The minimum value is going to be the smallest y value, which is going to be down here. So it's going to be -3. So the answer to this one is -3. The minimum value of k is -3. We're talking about the y values. The minimum value of k is -3. And then it says, well, what's the minimum value of the inverse of k? What is the minimum value of the inverse of k? Remember, with the inverses, the x's and the y's are flipped. So on the inverse, what was the y's will become the x's. What were the x's will become the y's. So on the inverse, the x's and y's are flipped. And this is saying, what is the minimum value of the inverse? Well, that is saying, what is the minimum y value on the inverse? But we don't have the graph of the inverse. All right, we don't have the graph of the inverse of k. We just have the graph of k. So we just can't look at the y values. So what you have to do is you have to keep in mind that the x's and y's are going to be flipped. X's and y's are going to be flipped. So if I'm looking for the smallest y value on the inverse, I go to the k. I go to the k function, and I actually look for the smallest x value. Look on this graph. The smallest x value is -4. So if I was to take the inverse of this, graph, look what I have. This point right here is -4, 3. Okay, so that point is -4, 3. On the inverse, it would be 3, -4. And that would be your smallest y value on this graph if I was to take the inverse of it. And that's what I want. I want the smallest y value on the inverse. It's going to be -4. I hope that made sense. I want to go through it one more time. So that's going to be -4. I mean, of course, it's a video, so you just rewind it and listen to me say it again. But I'll repeat myself anyway. What is the minimum value of the inverse of k? I don't have the graph of this. I don't have the graph of this. I have the graph of k. But you just keep in mind that the x's and y's are flipped. So if I'm looking for the smallest y value on this, I'm actually going to go up here and look for the smallest x value. And the smallest x value is -4. So if I was to take the inverse, this would become the y, and -4 would be the smallest y value. So this is -4. Let's go down to B. Find the inverse of k evaluated at 6. We'll do that one first. The inverse of k evaluated at 6. Well, this is the k function. But you just got to remember, on the inverse, I'm going to flip the x's and the y's. So here's how I'm going to think about it. Look at the point right here. If I put an 11 in, a 6 comes out. If I put an 11 into K, a 6 comes out. So this point right here is 11, 6, which means on the inverse, I flip it. So the inverse would be 6, 11. On the inverse, if I put a 6 in, an 11 comes out. And that's what it's asking. It's saying, what happens when I put a 6 into the inverse? Well, an 11 comes out. So this is 11. And let's go ahead and look at this one. Same thing. What is the inverse of K evaluated at 4? So look at this point right here. This is the K function. And I can see that when I put a 6 in, I get a 4 out. So this point is 6, 4. So on the inverse, you're going to have the point 4, 6. Which means on the inverse, if I put a 4 in, I get a 6 out. And that's what it wants. If I put a 4 into the inverse, what do I get out? Well, a 6. So that's going to be 6. Let's keep on going, see what we got here. Might not do all these. I think it might start get a little repetitive here in a second. Example 3. The function f, so this is the function f, is defined over this interval. This is the inverse of f. That's what it's saying right here. This represents the inverse of f. What is the maximum value of the inverse of f? So I'll let you find that. It's the same concept that we had here when we were doing these two. So what is the maximum value of the inverse of f? And then you're also going to find these. Same thing that you saw in the previous problem. Same thing as you saw. But let's talk about this one, because we haven't seen this one yet, but we did talk about it. What is the domain of the inverse of f? This was at the beginning of the notes. The beginning of the note said that for inverses, we switch the x and the y. So the x becomes the y, and the y becomes the x. But we also switch everything. So the domain becomes the range of the inverse, and the range becomes the domain of the inverse. So not only do you switch the x and the y, but in so doing, you also switch the domain and the range. All right. So keeping that in mind, what is the domain of the inverse? Well, the domain are the x's. What x's can go into the inverse? What I do is I go to f. That's not the inverse, that's just function f. And I look at the range of f. Because I know that the range of f, remember range is the y's, the range of f is going to be the domain of the inverse. Because you got to switch them. The range of f is going to be equal to the domain of the inverse. So what I really need to find is what is the range of the original function. Well, the range is the y values that come out of the function. So we can see that it starts at -3, start with the lowest value, include the -3 because you have this, a solid dot, and go to 7, and include the 7 because you have a solid dot. That's the range of your original function. So it must be the domain of the inverse. And let's go ahead and write it. The domain of the inverse is going to be -3 less than or equal to, because we want to include it, x, because we're talking about the domain of the inverse is less than or equal to 7. So the domain, that's your x's. The x is between -3 and 7, including the -3 and including the 7. So make sure you do these two. let's move on to the last one. And I think this is all stuff we've done. But let me read over it and just make sure that's the case. The function g, that's this function, is defined over the interval from -3 to 10, as shown above. Let the inverse of g, well, I don't know why it keeps on saying that. We know that's the inverse. This is the inverse of g. Values of the increasing function h are in the table above. So this is h. That's your h function. And you have to find the following if possible. So let me run through, I'll probably run through all of them just to make sure I've covered everything. So g of h of 6. Find h of 6 and then put it into g. Here's your h. I put a 6 in, a 10 comes out. So h of 6 is 10. So this is actually g of 10. This means I'm going to put a 10 into the g. Well, this is g. When I put a 10 in, a -1 comes out. So this is -1. And that's your answer. Let's go to the next one. G, inverse of g evaluated at h of 0. So the first thing I got to do is find h of 0. I put a 0 into the h. 0 into the h, a 3 comes out. So h of 0 is 3. I'm going to find the inverse of g evaluated at 3. I'm putting a 3 into the inverse of g. Well, this is g. That's not the inverse of g. That's just g. And here's how I'm going to think through it. See this point right here? If I put a 4 in, a 3 comes out. So this point is 4, 3. So on the inverse, let me put that point again. That point is 4, 3. So on the inverse, you switch it, 3, 4. On the inverse, if I put a 3 in, a 4 comes out. Well, that is the inverse. If I put a 3 in, a 4 comes out. So that's going to equal 4. Let's go to the next one. The inverse of h evaluated at g of 8. So the first thing I got to find is g of 8. I'm going to put an 8 into the g function. Well, this is the g function. If I put an 8 in, a 0 comes out. So g of 8 is 0. So this is going to be the inverse of h evaluated at 0. So I'm putting a 0 into the inverse of h. Well, this is h. It's not the inverse. That's just h. I need to put 0 into the inverse. Look at this point right here. If I put a -1 into h, I get a 0 out. So it must be the case if I put a 0 into the inverse, a -1 comes out. And that's exactly what I need to know. If I put a 0 into the inverse, what comes out? Well, a -1. And finally, this one right here. This one is saying the inverse of h evaluated at the inverse of g evaluated at -1. So I'm going to do this part first. I'm going to find out what happens when I put a -1 into the inverse of g. Well, this is g, not the inverse, it's just g. And I need to put a -1 into the inverse. So look at this point right here. If I put a 10 into g, a -1 comes out. I flip the x and the y, so on the inverse, I must have -1, 10. Which means if I put a -1 in to the inverse, a 10 comes out. And that's exactly what it wants to know. If I put a -1 into the inverse, what comes out? Well, a 10. So I'm going to replace what I just circled with a 10. And I'm going to say, I now want to know the inverse of h evaluated at 10. So I'm putting a 10 into the inverse of h. Well, this is just h, not the inverse of h. It's just h. And look at this point right here. If I put a 6 into h, a 10 comes out. So it must be the case if I put a 10 into the inverse, a 6 comes out. I just switch them. And that's what this wants to know. If I put a 10 into the inverse, what comes out? Well, a 6. And that's your answer. And I believe that got it. Yep, that is it. So there is a worksheet associated with these notes. Go ahead and do that for homework, and also do not forget to do these for homework as well. All right, I'll see you. Take care. Bye.